Hello, I'm Caroline Worden, the Fusion Energy Intern at American Security Project. Thank you for listening to this presentation. We're here today because we want to see fusion energy on the electrical grid. The United States and international fusion community have some large challenges to overcome. In order to have a successful fusion energy program, we need political will, good management, and sufficient funding. A challenge unique to fusion is that it has a very long time frame to completion. This long attention span makes it harder to get political will and lasting financial support. In fact, the U.S. fusion program has been around since the 1970s. Next slide. This graph shows possible paths to a fusion reactor from the 1976 U.S. Energy Research and Development Administration Plan with the expected dates of completion. You can see the blue line is the maximum effective effort ending in the 1990s, and the 1978 red line doesn't have a completion date, so this is the fusion never baseline. The actual funding is tracked under the projections. We're below the fusion never line. Let's look at the actual funding. Next slide. For the past 15 years or so, the United States has had a downward drift in fusion funding, but this wasn't always the case. In the 1970s, in response to the oil crisis, there was a bump in fusion funding. At that time, there were many fusion experiments scattered around the country, and there was more political support for fusion energy in Congress. Washington, New Mexico, Maryland, New Jersey, Massachusetts, California, Wisconsin, Florida, New York, and Tennessee all had DOE-funded fusion experiments. Then the program suffered budget cuts, and multiple experiments were shut down. Now the states that have major fusion experiments are California, Massachusetts, and New Jersey. Next slide. The U.S. has 3 large tokamak fusion experiments: D3D with General Atomics in San Diego, NSTXU at the Princeton Plasma Physics Labs, and Alcator CMOD at MIT. The largest U.S. inertial fusion experiment is the National Ignition Facility at Lawrence Livermore National Laboratory in California. We also have Omega at the University of Rochester, the Z Machine at Sandia National Laboratories, and the Nike Laser at the Naval Research Lab. Next slide. The U.S. is also contributing to ITER, the International Collaboration Tokamak being built in France. The U.S. contributes procurement of hardware, assignment of personnel, and cash contributions for the U.S.'s share of common expenses like personnel infrastructure, assembly, and installation. Next slide. Other countries are very serious about fusion as an energy program. China, South Korea, and Europe all have specific goals, timescales, and funding to have successful fusion energy programs. South Korea is designing a fusion power demonstration reactor in collaboration with the Princeton Plasma Physics Labs called K-DEMO. The country's National Fusion Research Institute has plans to complete it in the 2030s. South Korea is also running K-STAR, a superconducting long-pulse tokamak, and contributing to ITER. This country has strong political will for their fusion program. The South Korean Ministry on Education, Science, and Technology said in 2012 that developing technologies to build K-STAR would be a national priority for the next 10 years. This puts them on track to build a commercial fusion power plant between 2022 and 2036. Next slide. So why aren't we doing this? In part, because we have a low state of readiness to develop practical fusion energy. In the methodology called Technology Readiness Levels, or TRLs, fusion components are perceived to be rated too low to be talking about energy, meaning that even if we got great gain on an experiment, we wouldn't have a fusion reactor because the technology is not ready. The last time the U.S. made nuclear reactors, we went from the first reactor in 1942, this is Chicago Pile 1, to the USS Nautilus, the first nuclear-powered submarine, which was authorized in 1951 and launched in 1954. Less than a decade-long effort got the program to a working nuclear-powered submarine. Admiral Rickover was instrumental in managing that transition, and the path he set us on still defines the U.S. nuclear plan. We have the problem in fusion that, in part because of low TRLs, fusion is thought of as a science experiment, not an energy program. The level of seriousness is not high in the U.S., and the focus is no longer on fusion energy, but rather on fusion science. Next slide. Our experiments are housed in two different offices. Magnetic confinement experiments, like the tokamaks, are housed in the Office of Science, and the inertial confinement experiments, like NIF, are housed in the National Nuclear Security Administration. In the Office of Science, the United States has no plans to develop a comparable superconducting experiment in the next 10 years to the Asian superconducting machines. This was stated by the FES director, Ed Sinikowski, at the APS DPP meeting in summarizing the strategic plan that FES is developing for the next 10 years. Now, preparing for a fusion nuclear science facility was proposed in the FESAC report to provide science and technology understanding for informing decisions on plasma confinement, materials, and fuel cycle concepts. You'll note that the wording is preparing. There are still no plans to build this in the next 10 years. Now the question is, how do we get the United States back on track to have nuclear power plants, preferably within our lifetimes? The American Security Project has written a report on how to better organize the U.S. fusion program, and I invite you all to read it here. Thank you for listening.